Mutta sitten ei saa tätä pömpeliä tuohon näkymään. Et aikaisemmin on tehty niin, että kun striimataan YouTubea, niin näytetään sitten tämän tietokoneen kautta. No nyt se näyttää erilaiselta jo. So this looks better, right? Yep, that's the best we can do. 5 seconds latency. What about now? Is it okay? Yeah, I think it is okay. So for online participants, we're gonna get started in a few minutes. I need to apologize this inconvenience, but we are experiencing difficulties in the overhead projector in the classroom. So Mustafa, what do you say? Not good. That's my picture. Oh, you mean the left and right side?
No, here, like, is it because of the green screen?
I think so, yes.
So should we take it a little bit?
No, it's okay. That's okay. That doesn't matter really.
Okay.
Yep. Hey, so are you all able to see me through the YouTube? So can you see me through the YouTube? You can. Because what you need to do is that you need to log yourself in the YouTube channel because this overhead projector is not working. Oh, se toinen. Okei. Okay. Oh. Niin, just sä kehuin, että täällä on kaikennäköistä tämmöistä hienoa, mikä ei toimi. Mutta on kyllä hienoa. Näkee esimerkiksi, jos verkon painona, nämä on ihan, oman kautta niin kuin ihan tosi hyvä kyllä. Se painaa. Joo, näin on, joo. Oho. Seiskasalit. Okei. Okay. Niin, se on niinku, tää niinku meillekin niinku tämmöistä kokeilua, että toimii ja ei toimi. Niin. Niin. Niin me striimataan tuota YouTuben kautta, OBS. No se on se toimiva systeemi. Se on nimittäin aika iso yhteisö, se OBS-yhteisö. Se on se kaikista yksinkertaisin systeemi. Mutta se on ongelmallinen, kun se on ilmainen ohjelmisto. Ne ei voi käyttää rahaa mihinkään. Mutta nyt vois. Nyt kun niitä on semmosia lisäpalikoita, mitkä on maksullisia. Nyt rupes kiinnostaa.
Milloin ase?
Ei mitään, me mennään silleen, että nämä ihmiset katsoo mua YouTuben kautta. Tää on niinku ihan hölmöä, mutta minkäs teet? Tai niinku helpompi mun olla luento kuin tuolla omassa kopissa. Kuin tässä. Joo, ne on varmasti, kun ne on silleen hienosti rakennettu, niin ne on mitä on. Mä otan tämän pois kokonaan tän. Okay, so here's the deal. So we are not going to make this projector to be able to cooperate with us today. So just not possible today. So the way you can follow me today is that you just need to log yourself to YouTube channel, and that's it. But we do have another problem here too, because I'm using my this computer, and the keyboard of this other computer is again not willing to cooperate, so I'm unable to log myself to this computer. That's why I don't see if there's any comments, any questions from online participants. You guys need to help me. So if there's something that somebody's asking, let me know, because I cannot see it. Okay, so how do I look in YouTube? Am I looking young, strong, fast?
Too big.
What?
Too big.
Too big?
Yeah.
No, I don't want to look too big.
You should stop
Ah, you mean my muscles are too big? Here's the guy that I love so much. Hey, thank you guys. We're gonna close roughly at a little before 2 o'clock. Hey, because that's simply because we left behind from the schedule, and we only have one more week to go prior to midterm exam. There are so many things that I need to cover prior to midterm exam, so that's why. Okay. Yeah. Thanks, Mustafa. All right. So you see the you see the first slide, right? Okay. You see where is that we are at, and we are not that much left behind as shown in the first slide because 3 weeks back we got the visiting lecturer from Delft University of Technology. So there was a Professor Emeritus Aren Swap that delivered the lecture about the bicycle dynamics. And then a week ago we discussed about the career counseling. Career counseling about how is that you can apply your master thesis project, where you can get the title, where you can get the topic for your master thesis project. And then some of you already, because I say that I'm able to help you guys, so if you need the reference later, I can offer a one for you. And I can do it. But now my inbox is not looking very good, so there's a very long queue, and you will get the response about the reference letter, but it will be on Saturday, Friday, Saturday probably. So don't expect to hear me today, not tomorrow, not day after tomorrow, Friday maybe, Saturday at latest. And yeah, and this goes for other students as well. So if you need a reference letter, I'm happy to help. And it's going to be something that I'm simply going to take a look at how is your grading from my classes. And then if it is a high, very high number, then I'm going to speak, your performance in my class. I cannot speak on behalf of other professors, and I don't know how is your performance in other courses than mine. Okay, fair enough. All right. Okay, so that's what comes in the emails. What we're going to do today is that we're going to speed up a bit. We're going to close the case about three-dimensional multibody dynamics. And for our visitors, you learn spatial multibody dynamics through the YouTube, I hope. And now this class, we're extending the spatial representation through, the planar representation to spatial representation. So from 2D to 3D. And it's not easy. It's easy to say, more difficult to do. And what makes it difficult is the rotations in three-dimensional space. And we learned this class that there are methods, such like the one that is based on Rodriguez equation and Euler parameters, that are based on 4 parameters. And their 4 parameters are describing the orientation of their body. And in a YouTube earlier, you have learned that there is a method based on 3 parameters, like Euler angles. But here we looked at the ones that are more advanced in the sense of computational stability, and those are the ones that are based on 4 parameters. 4 parameters, but the body can still rotate in 3 different ways. So these 4 parameters are not independent, but they are coupled via constraint equation. So that's what they are doing for us. All right, so we're closing the case of three-dimensional multibody dynamics, and then finally, flexible bodies. Flexible bodies, and flexible bodies, we're gonna take a look at the basics, and then I really want to rush myself to start describing about how is a finite element modeling. This is something that we're gonna take a look at the shape functions, polynomial expansions, and basics of the finite element method. All right, briefly. So we discussed about the Rodriguez equation. And Rodriguez equation is based on this concept that we have a vector like this one here. And then what we're going to do for this vector is that we're going to introduce a unit length vector v. And then we're going to take a hold of this assembly that is looking like this. And we're going to introduce a rotation that is amount of theta along this unit length vector v. And now when we're comparing the original configuration and final configuration of this vector here, we can describe the 3-dimensional rotation matrix that is then based on 4 parameters. 3 of them are describing this vector v, which is unit in a length. 4th is a rotation theta. But because this is unit in length, these three parameters describing this vector are not free to take any numerical value they want, because this is forced to be unit in length. So that's where the constraint is coming from. So that's the method that is based on Rodriguez equation. And then when you're using name game, when you call these components in different names, you can get something that is called Euler parameters. Euler parameters and Euler angles are not related. So they are a completely different story. Even the number of parameters is different, concept is completely different. Anyways, once you're using this name game, then you can get the four parameters that are called Euler parameters, and then the rotation matrix looks like the one that is shown in this lower right corner. And right now, even my pen is not willing to cooperate with me today. So everything is against me today, except Esral. Esral is playing in my team. Others are against me. And you guys, of course. All right, and even the pen is not here. Okay, then we learned how to use this in a robot kinematics. We learned that there is a method that is called 4x4 transformation matrix. Very boring name, by the way. How is it they did not figure out any better name than that? But it's a 4x4 transformation matrix, which is based on kinematics of this body reference coordinate system. It's that we're relocating the components of kinematics in a certain way, and that's it. That's all we need to do. And why this is important? Because this describes the relationship between the two neighboring coordinate systems, allowing us to describe the robot kinematics more or less automatically. That's the beauty of the method called 4x4 transformation matrix. And this the method that is most often used when we are using this 4x4 transformation matrix is called Denavit-Hartenberg. So it's like predefined parameters that you can use in Denavit-Hartenberg. And these predefined parameters are described in these two figures you can see in the left and the right. And there is a total of 4 different parameters. If there's something outside of this parameter space, then this is no go. Then you cannot use this description. But surprisingly enough, when you get used to deal with this 4 set of parameters and you are able to twist and manipulate your coordinate system, you can practically describe any robotic system using these 4 parameters only. 4 parameters only. And again, if you're not happy with that, you can go back to what we did a couple of weeks back. You can describe the method by yourself. Beauty is this. You can call it not Denavit-Hartenberg, but instead you can call it by your own name. Think about that. Aki's method of transformation. Already started to sound good. So it must be very efficient. So you can use your own name and make it happen this way. All right. And remember, this is based, again, sorry. So this is if you're not happy with these 4 parameters. So you can decrease the parameters as you wish. Everything is possible. Now, the beauty of Denavit-Hartenberg is that you need to create this table shown in the lower right corner of this slide. Table that describe the different kind of the robot systems. And once you have a description of 3 different bodies, like in this example here, rest is substitution. You just substitute the parameters from one coordinate system from number 1 to number 2, number 2 to number 3, and all that happens with help of this table you see in the lower right corner. So the only complication here, only difficult matter here is to create this table here. But once you have a table, rest is downhill. So that's how it goes. All right, and sorry about this because we're going fast because we discussed this already a little while ago. And you can catch up by taking a look at the YouTube channel that is that where this recording will appear as well. Okay, then something surprising, something that is only valid and big problem in a 3-dimensional dynamics, and that's the fact that if you have these generalized coordinates and rotational parameters that are describing the generalized coordinates, they are not the same than angular velocities. It's just not being possible to find this kind of the tenorize coordinates that are same time angular velocities. This is not being possible. Now, what I learned very recently that there is this something that is called Lie group, which becomes to be close to solve this problem. But the Lie group is a like whole different mathematics. So it's another branch of mathematics. But if you really want to commit yourself, you can actually make a nice papers about the Lie group and how it helps to describe kinematics. But it's really, like I say, it's an own mathematical branch. It's pretty advanced mathematics, so it's challenging in that regard too. But what we do, what the others are doing, is that we are introducing relationship between these rotational parameters and angular velocities. And this relation is this famous T matrix. T matrix that depends what are the parameters you're using. Because of course, T matrix have a different dimensions depending what are the parameters you use. Because Euler angles is a 3 parameters, Euler parameters are 4 parameters. So matching these two things, you have to change the size and dimensions of the T matrix. Example you see in this slide here is that how is it you can relate rotational parameters and angular velocities when using Euler parameters. You see that this is 3 by 3. But if you have Euler parameters, then it will be 3 rows, 4 columns, because of 4 rotational parameters. All right. So that's how it goes. Now, this is the beauty. I mean, that sounds like, could I care less? So what? What difference this makes in my life? Well, actually, it makes a difference in your life because now you have a tool that you can compute your dynamics using any generalized coordinates you want. But same time, you can describe your inertia properties using body reference coordinate system because the T will combine them together. So that's the message that I would like you to learn, nothing else. All right, then comes a very involving mathematics when we are looking at the particle velocity. This is now based on the T matrix, and we learned the skew-symmetric matrix, skew-symmetric representation, which is basically a cross product expressed a little bit a different way. You familiar with the skew-symmetric matrix representation? So you know it. Very good. Okay, so it's just that the cross product can be expressed by using a skew-symmetric matrix. Like you see in our upper right corner of my slide, the angular velocity is expressed by as a cross product. But mathematically, the manipulation of cross product is almost no-go. So it's very, very difficult. So instead of using cross product, we're using a skew-symmetric matrix representation. Okay, so finally, when we look at the velocity, and I'm gonna, like I say, I promise I speed up. So the velocity of a particle can be seen to be consist of 3 components. Excuse me, 2 components in a spatial case: translational velocity and the one that is describing rotation. Angular velocity, that's the way you wanted to express it. But we don't want to use angular velocities because we would like to use the parameters that we're solving. That's why equation that you can see here, yeah, I cannot touch the screen because it jumps in correct place immediately. The one you see here in the lower part of the slide. When we continue, when we're expressing the acceleration, so it's again the same thing. So it's just more complicated. 3 components like it was in the case of planar kinematics. That's it. Now, if we wanted to express acceleration by using generalized coordinates, that becomes to be nasty. Like you see that in the lower part of my slide when I'm expressing my acceleration, not using angular velocities or angular accelerations, but instead rotational parameters, it becomes to be very nasty looking equation. Forget about that because we don't need to look at the details. You just know that it's possible, it's doable, and that's it. And it's doable because, again, because of this magic T, nothing else. All right, the T now finally comes handy when we're looking how is the inertia, or generalized inertia forces. Generalized inertial forces is something that we first look how is the inertial forces in global coordinates, and we mapping that representation to be expressed by using generalized coordinates. How? Well, with help of virtual displacement. And again, I'm not going to take a look at the details here. I know that my inertial force is a mass multiplied by acceleration. As it is mentioned here in the upper part of this slide, mass is now integrated over the volume of the body, over the density of the body. And then the acceleration is the one that we looked just a little while ago. And that's it. Now, when we're using this virtual displacement that is can be expressed using this partial differentiation, I can do the mapping. That's my magic mapping matrix. Now, using this mapping matrix, my generalized inertial forces look like the one that is shown in the bottom part of the slide, and then comes the many substitution, very nasty substitution, which you should just do it. No thinking, just a substitution. And then you see how the inertial tensor started to look like. And this it is. This is it. Now, a highlight here. I have here mass multiplied by acceleration and quadratic velocity vector. What I would like you to see is that the mass matrix, which is located in the lower right part, which is a T bar multiplied by U bar, multiply U bar transpose multiplied by U bar transpose, and those are Q-symmetric forms, and then the vector T bar. What is in the middle? This Q-symmetric form of U bar transpose multiplied by Q-symmetric form U bar, that's going to be your inertial tensor. And now with help of the T, you can describe that by using any set of generalized coordinates you want. So it's very mechanical, even though that it looked very bad, but it's very mechanical. And the one that is beautiful here is that the last equation of this slide. So T bar multiplied by inertial tensor multiplied by T bar. That's it. An inertial tensor is exactly what I just explained to you. This is how you can compute it, but you shouldn't. You should take this information from CAD software because it does the computation automatically. This is serious volume integral over the boundaries of the body, so I don't recommend you to do it. So it's too complicated. So please use a CAD software for that purpose. These are the components, how they look like. So I have mass product of inertia and mass moment of inertia. Mass product of inertia is located in off-diagonal components. They can have any sign depending on how the body coordinate system is located at. Mass moment of inertia is always a positive in the sign. And then finally, the equation of motion, we can force equation above to be equal to 0 by using two different techniques, either substitution or by using Lagrange multipliers. And we want to use Lagrange multipliers, and then it's going to be like the one that you already know. No difference in that regard anymore. That's how the equation of motion look like. Now, our visitors, I recommend that you don't get started here in a three-dimensional multi-body dynamics, but instead you do models that are related to planar cases. As soon as you're ready with your videos, let me know, and I will give you assignments. I will give you simple mechanism that I'm hoping you to create the equation of motion like the one that is right below the ODE. Solve it using the MATLAB, and then you're going to be happy. I will be happy. You're not going to be happy, but I will be happy, and we'll see. And then I will ask you to do, because you're doctoral level students. So doctoral level students, that's not enough. Rest here in the class is a master level student, so you need to go beyond of that. So then I will give you another way that you can create the equation of motion. But first thing first is solve to create the equation of motion using this ODE based on Lagrange multipliers. A lot to digest, a lot to learn, a lot of videos to look at, but you can do it. Okay, and you have, of course, you have the big brains with you, so you have Esral. If any doubts, any problem, here's your guy. He can help. All right, now, finally we're moving on. So we go with the flexible bodies. I'm going to take just a little bit of time for introduction. And then the main body will be how is it we can use this magic method called floating frame reference formulation and where the floating in a name comes. Why that is called floating frame reference formulation? Because floating, as the title implies, is a coordinate system that is not rigidly attached, but is floating with the body. What is that? How can something can be floating with the body? So it's either connected or not. And this is not connected, but it's still floating with the body. How come? That I'm going to explain to you next week. I hope next week. All right, rigid bodies. You know the story already. There's no such thing like rigid bodies. That's urban myth. That's non-existing thing. But most of the cases, very often, the body deformation is insignificant in terms of dynamic performance. You can ignore it. But sometimes when you want to make more accurate models, you must take that into account. And then we're going to take a look at the ways how you can take that into account. And we're going to take a short look about this method you're already familiar with, landmass approach. And then we're going to take a look at another approach, which is the main body of today's lecture, which is the floating frame reference formulation. Floating frame of reference formulation. First in-class quiz. That came a little bit of surprise to me too. Okay, in-class quiz is this. When a body deformation needs to be accounted in the multi-body applications, when the deformations, let me explain this to you first. And the first thing that I need to do is that I need to put the Socrative on. You don't have an access to this, so you just need to follow what we're doing. Squeeze, lounge squeeze. I'm not sure if this is the one that I need to take. I first need to look at this, what is a squeezes. Now I need to be careful because you can possibly see the correct answer. So, lounge. No, not this. Absolutely not this. Okay, so I need to take this this place Audio, I think I accidentally clicked this audio. Yes, I accidentally clicked the audio to be muted. Yeah, it works. Sorry, my mistake. So online participants, my apology because I accidentally clicked something that was my mistake. What you guys can see at the moment, video capture device, or window capture device. Okay, what you see at the moment, is it okay? Is it something that is a slide? All right, very good. All right, like I said, the flexible multi-body dynamics can be categorized to two different fields. One field is where we are assuming deformation to be small. That's where the strain displacement relationship is. It's not. Hmm, I got it. I got it. I don't want to show that because I want to show something else. Yeah, I see. Okay, what about now? What do you see now? My OBS? What about now? Yeah, thanks. Thank you very much. Very annoying. What we're gonna do? Okay, you understand that we are in a University of Technology, and because University of Technology, we cannot, by the law, to make these technology gadgets to work for us. I guess. I don't know why, but it seems to be difficult for us. Okay, this is what I wanted to show. Okay, two fields, small deformation and large deformation. Now those are defined how we're taking strain displacement relationship into account. Displacement. What's the displacement? That's the difference between your reference motion and the deformation. Reference motion is easy to think that that's the rigid body motion. And the deformation is where the body is actually located at. So if this is where the body is rigidly, and where it is actually is deformation like this difference, that's called displacement. And displacement is a function of the location because it's different depending where you are at in your body. At the end is the largest if you look at the cantilever beam, and here in a close of the cantilever is the smallest. But it's a function of the body location. All right. This displacement is related to strain. And if this relation is linear, then you can only describe the deformations that are small. Small means that you don't have an interaction between the axial motion and the deformation, meaning that if you have a cantilever beam like this, if you load it heavily, this end will stay in a loading line. So it will go down here, which I cannot do with my hand because it's unrealistic. In large deformation case, the relation between strain and displacement is nonlinear. That means that if I can introduce a lot of forces here, the deformation will be such that there's a minor displacement in my axial direction. And this you can only take into account when you have a large nonlinear description of strain displacement relationship. What we're going to do in this class is that we're going to focus on small deformation. Finite element modeling is capable to do both easily. So it can do a large and a small deformation. But when we look at this, something that is related to vibrations. The vibrations, what we are looking in this class are something that are linear vibrations. So we are not taking this nonlinearity into account. And in this class, we're going to focus on small deformation cases only, nothing else. All right. Okay, so this is a more explanation. You see that in the lowest case, last picture, the force is so large that the end is moved a little bit on axial direction. That this is something that you can take into account only if you have a nonlinear strain displacement relationship. And here you see the two cantilever beams. The one is assumed to be linear strain displacement relationship, other one is nonlinear. And of course you understand that the one that is closer to you is nonlinear because then the end of the cantilever is moving in like this kind of the curved path, and because of the curved path, the pendulum started to do the motion in axial direction. Other case is small deformation. They look alike, so there is not the significant differences, but the conceptually they are completely different. All right. Now, landmass approach, like I say, like I promised, I'm going to be very fast here because this is something that I introduced in my fall class already. So basically the idea is that we have a rigid body. It must be a beam-like body. It can be a plate-like body, but basically it needs to be a beam-like body. And what you do for that beam-like body is that you are dividing this one body to number of rigid bodies, each of them connected by using the spring element. Problem here is that these springs and masses, they have a very different natural frequencies. Remember we discussed shortly last year about numerically stiff systems. You still remember what that is? That is a system that consists of frequencies that are low and frequencies that are high. And this is a big problem for numerical time integration scheme. It's not a problem if all the frequencies are high or the frequencies are low. That's okay because everything can be scaled in a way that computation will be efficient. But it's a big problem if you have small different frequencies and high frequencies. That's going to be something that the computer simulation will suffer. You want to avoid it as much as possible because it will make your computation to be slow. Why? Because computer simulation understand that there is this high frequency simulation, high frequency oscillation here. And it started to tune its time step such the way that this high frequency oscillation that is typically not important for us is accounted. And it's tuning the time step to be very, very small, and that's what kills the computational efficiency. So what you wanted to do is that you want to avoid the cases where there are high frequency and low frequencies. And the one way you can avoid it is not to use a landmass approach. Because landmass approach, think about the beam, think about the bending frequency. That's low. Let's say 50 hertz, less than a 50 hertz. But if you think about the axial frequency, very high, 1000 hertz. Here it is, 1000 hertz, 50 hertz. That's your problem because your time integration scheme will recognize 1000 hertz and it tunes itself to take these 1000 hertz into account, but even though that we don't care about it, because otherwise it can go unstable, and that's going to be a big problem too. Okay, yeah, it can take a different kind of large deformation into account if you keep on adding the number of rigid bodies, but still a little bit artificial. Here is a couple of videos. This is where you see the wire rope. It's let me see where the wire rope is traveling now. Yeah, there is this hook that is moved close to the box. And the wire ropes are modeled by using this technique that is based on landmass approaches. And you can see that even this taut string effect is accounted. You know what this taut string effect is? Something that, I don't know if you guys are playing a guitar. You play a guitar or no? Okay, what you do in a guitar is that there are these strings. How you can tune your guitar is that you can introduce more strain to these strings, more loading, preloading. And based on the preloading, the frequency will change. And this is what you can see in the cables too. Because the cable, when there is just a hook, have a very low frequency, but as soon as you introduce axial loading, the frequency will change. It makes this like a high frequency translational vibration. That is called taut string vibration or taut string effect. Okay, here the cable model is based on landmass approach. Here's another video which is more than 25 years old. This is the crane that we still have in the lab. And now the crane is modeled by using this landmass approaches. And that's how the flexibility was accounted at that time. Still, landmass is okay in the cable models. There are better cable models available at the moment, but it's okay. It is okay approach. Okay. All right, computational expensive, that's what I already mentioned. So it can lead to stiff system. It can be applied for beam-like structures only, or mainly. Material damping models are not very advanced. but it is easy to implement. Theory is very simple, but that's not what I'm trying to explain it here. Ah, another in-class quiz. Okay, numerically stiff system means what? That the system contains low and high frequencies, that system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. Four choices. Visitors are voting what? Your vote goes to. Oh, is it on? No, not on. Okay, hold on. It should be on now. By the way, what is that you see at the moment? Can you see the Socrative in your? Yep. Okay. So the screen view is such that you can see the Socrative. Right. Very good. Okay, visitors, what you are voting? Numerically stiff is that the system contains high and low frequencies, or that the system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. Your answer goes to A, B, C, or D. D. Okay, so visitors are voting D. Some of the bodies are assumed to be flexible, and the rest are saying, okay, I got that last time it was 13 answers. And now I got 13 answers. I think that I'm okay. So can I just go? You guys are all done? All right. So the distribution is this. 73, so it's very good. The correct answer is that there are high and low frequencies. Because the high frequencies and low frequencies simultaneously is a big problem for integrators. Big problem. Okay, moving on. Back to my slides. Now we're going to take a look at this floating Fermi reference formulation, and we're going to take a look at the description of deformation, and I think we have a time to do that as well. All right? Now, the floating Fermi reference formulation, few notes before we jumping into the topic, is taking the best out from the finite element modeling and from the multibody system dynamics. You know, the multibody system dynamics is very good to describe this large translation, large rotations. There's something that we can call reference motion. It can be, I think it is almost okay to say that it is rigid body motion. Even though that I heard these argues that, okay, there is no such thing available here, right, rigid body motion. Okay, yeah, I understand that, but you understand if I say rigid body motion and when I call it as reference motion, those are the same thing. Because human brains are easier to understand rigid body motion than unclear reference motion. Okay, rigid body motion. That's where the the multibody system dynamics is very good at. Finite element modeling is very good at to describe small deformation with respect reference coordinate system. So what we can do then is that we can take this ability to describe large translation and rotations and combine that with this ability to describe small deformation with respect to this reference coordinate system. That's all we need to do. So it's basically we take a finite element model that is discretized to small elements, and we started to describe that with respect to the coordinate system that is translating and rotating. It is that simple concept, but it comes with the certain complications. And the complications are the fact that, you know, the concepts in finite element and multibody dynamics are a little bit different. And then the big problem is that, you know, we need to take these inertia forces into account. So we need to use multibody dynamics as a part of the finite element method, and that comes with a certain complications. It's doable, but it's a beautiful method. And then the big problem is that a typical finite element model consists of at least 1,000 degrees of freedom, 10,000 degrees of freedom easily, 100,000 freedom, 100,000 degrees of freedom, why not? And now the reference motion is described by using 6 coordinates, 7 coordinates max when we're using Euler parameters. Now 6 coordinate versus 100,000 is not good relation. So 1 is too many. And what is too many is a finite element model. So we need to do something for that finite element models. And what we can do for them is that we can reduce the number of unknowns, number of degrees of freedom. And that's something that we cannot do by using this model reduction technique, something that Jussi Sopanen is teaching you already, what is his class? This semester? Machine dynamics. Okay, you know that Jussi Sopanen is not called, Professor Jussi Sopanen is not called Professor Jussi Sopanen, but Professor Jussi Model Reduction Sopanen. So his middle name is model reduction. So he knows the model reduction back and forth. And he recognizes if you say, hey, model reduction, what do you think about this? Yeah, well, why not? He knows it. He knows it for sure. And now this is what we're going to do. So we're going to first combine. We're going to put together finite element modeling, multi-body system dynamics, and then we're going to use the model reduction for finite element. That's it. But because it annoys me that often the finite element method is explained to students in a way that there is this springs, and then we have these nodal locations, and something that is not between the nodal location is empty, is a black box. This is completely against the concept of finite element method. Finite element method is all about what is between these nodes. It's all about that. That's why I would like to take a few minutes to explain how is the nature of finite element modeling. Because it gets started by describing what is between these nodes. Using polynomials, or if you're not happy with the polynomials, you can use something else. But it's important to describe what is between these nodes. Then once you know the life between these endpoints, then you can describe these endpoints, but not other way around. So finite element method is all about what happens between the nodes. And we're going to take a look at that, and that's going to give you, and I'm going to also introduce the method that is called isogeometric method, which is not based on polynomials. You know, finite element method is basically based on polynomials all the time. So this life between these points is described by using polynomials. But polynomials are problematic because some of the geometrical shapes are difficult to describe by using polynomials. So you can make it better to describe some of the geometrical properties by using B-splines. Non-rational B-splines would be the best, called NURBS. And some people are, instead of using polynomials, they're using NURBS, which is okay too. But again, it's all about what you're describing or what you feel that is between these nodes. It's all the time that. So that's how we're going to get started. And first thing first is this. You know, the floating frame reference formulation, it is now based on the new kinematics. So we have to change the kinematics. Very bad news. Because remember what we did in the very beginning. So we said that these are our kinematics, and we cannot change it afterwards. Now we're going back to the beginning, and we say, hey, instead of having this kinematics where we have a u-bar, we have u-bar 0, which is describing where the particle was, and the u-bar f, which describes this displacement. Now, because the kinematics is changed, everything needs to be redone. We have to do everything again. Constraints, inertia forces, so on and so forth. But we are not going to take a look at that. We're just going to know that the kinematics will be different. And then I will give you what it means, how it's going to look. But we're not going to take a look at the details anymore, because if you wanted to torture yourself, you can take a look at the lecture notes. All right, but nothing else. Right, so now we have here a new kinematic equation, which consists of capital R, describing what's the relation between the global coordinate system and the body reference coordinate system. Then we have a rotation matrix describing three-dimensional space. And then we have a vector u bar 0, which is describing where the particle was when there were no deformation whatsoever. And then the displacement. And again, displacement is different depending where you are at in your body. Remember this cantilever beam? Cantilever beam, when you look at the displacement, is very large in this end, free end, becomes to be smaller, 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 until it's zero, where the beam is connected to ground. So it's a function of the body location. Now, this almost implies that, okay, because the vector u bar f is different now every location you go in your system. So it means that this u bar f is having infinite number of locations to describe. And we cannot do that. We just cannot do that because we have a finite computational resources in our disposal. So what we need to do is that we need to look at the certain points of the vector u bar f. And these certain points will be nodal coordinates in your finite element model. Nothing else. Rest is kind of accounted because we kind of know what happens between these nodes, but they're based on the assumption, how is your elements. And that's how we're going to do. All right. So like I said, we're going to take a parts of finite element modeling, a parts of the multi-body system dynamics. That's what is called floating frame reference formulation. And it can be used for a wide variety of applications. This is something, maybe yes, remember, this was a very early developments for maybe our company when we look at the spatial bodies, how is that they deform in different cases. This was a three-dimensional crankshaft. And you see that the connection rod was described as a flexible bodies. This is something that Dr. Pasi Korkealaakso was involved about the sliding joint. Sliding joints. Sliding joint is still very unpleasant to describe by using these modes because their contact points keep on changing all the time, as will the frequency and the properties of the structure. Okay, that's a floating frame reference formulation. Now we're going to first take a look at the first part, which is this deformation. All right. And we're going to take a look at the finite element method. Finite element method is a foundation here. How many of you knows the basics of finite element method? You guys, you're familiar with the polynomials? Not polynomials. Loading cases. Okay, very good. So what course was this polynomials? Was it Marcos course or who was the teacher at that time? I don't even know. Timo Pierre. Okay, very good, very good. That was a bachelor level course? Okay. Maybe for you guys it's going to be too simple thing, but we'll see. Okay, so we're going to get started in this finite element method, which is a method where we divide the structure to small elements. These elements are not representing the correct solution, but the piece of solution. When you keep on adding these piece of solutions together, you can get the better and better solution. So this is called convergence. Finite element solution, when you use an overly low number of elements, is typically too stiff. Not necessarily, but it's typically too stiff. But it becomes to be more and more accurate when you keep on adding the elements. And this, how fast you can get the acceptable solution is called convergence rate. How many elements is needed to get the acceptable solution? Heavily case dependent, because different cases needs a different number of elements to get acceptable solutions. But again, this is something that is a feature of finite element modeling. You can improve the accuracy by adding the elements. You will compromise that computational efficiency because more element, more unknowns, more computation you need to do. So that's the nature of finite element modeling. Okay, these small elements are connected together in the nodes. These are these points that I mentioned you earlier. These are these points that you can get the displacement. You can get the clear physical interpretation. What are the displacement in this nodal location? And elements are connected together in these nodes. Now, finite element model itself look like a fishing net, depending what kind of elements you're using, because there are different kind of elements. But if you use a plate elements, then the structure look like something that there's a structure, top of which there is a fishing net. And these corners or these rectangulars in the fishing net, those are the elements. And they are connected together in another locations. So that's what the finite element method is about. All right, then the questions that I will ask are listed here. Explain how polynomials can be used in the approximation of displacement in the finite element method. Then role of Pascal triangle in a finite element method that is related to polynomials and is related to convergence rate in certain cases. What convergence rate means in finite element method. Now, based on your experience from the class you mentioned, are you already able to answer those three questions? More or less.
I just checked the bachelor's degree courses, and there is no talk about Pascal's triangle.
Okay, so others than Pascal's triangle, you can do it.
Yeah, but 16 and 70 it has. In steel structure, in my courses it has.
So what was that?
Steel structure.
Steel structures.
Yes, yes, it has. We have assignment like this.
Very good, very good. So those ones that are selecting the specialization of steel structures, you already know the basic of finite element model. I would say that that's a good news for you. We are not going to spend that much time in the basics of finite element method, but it's a good that you can refresh your mind about what's the basics, how the polynomials goes. All right. Or the Pascal's triangle is important too. All right, let's take a look. So let's take a look at this polynomial business. And we're going to get started from the most simplest element you can think of. So the element that can only get shorter or longer. Spring, if you may. Spring element. And the spring element is something that consists of two nodes. There's one node in both ends of the spring elements. These nodes, one in left-hand side and one in right-hand side, they can only move in this longitudinal direction, meaning that this node here only have 1 degree of freedom, and this node here has a 1 degree of freedom because it only can move this direction, plus and minus this direction. So no motion in transverse direction is allowed. So this is maybe the simplest possible element that this is when I get started to explaining the role of the polynomials. Okay, what we do in a finite element modeling is that we're going to describe the displacement in all the points in the element. And let me emphasize this, all the points in the element. So this displacement, remember when we look at the cantilever beam and displacement in a cantilever beam, you notice that it's changing as a function of the body length, beam length. Now, same also in the spring elements. So the displacement even in the spring elements is not constant, but is varying depending how you're introducing the displacement. Are we going to describe this displacement in not just in an end location, but all the locations between these endpoints by using a polynomial? Now, because we have here 2 degrees of freedom, so we are limiting ourselves to using just the 2 polynomial coefficients, just 2. But soon we're going to take a look more advanced, so we can have more advanced, more complicated polynomials. So 2 polynomial coefficients that are A1 and A0. And now if I would be able to solve the A0 and A1, that would be my solution. That's all that I need to know in a finite element modeling. Problem is that they don't represent anything physical, so the physical interpretation is non-existing, making it hard to use it this way. So what we wanted to do instead of using these polynomial coefficients A0 and A1, we want to use a nodal displacement, because nodal displacement have a clear physical interpretation. This is it moving left or right? This is it moving left or right? So it makes sense, whereas the polynomial coefficient makes no sense. I mean, making sense, but not having a clear physical interpretation. Now, what I wanted to do is that I wanted to replace these polynomial coefficients by nodal displacement. How can I make that happen? Well, I can make it happen in a way that, if you look at the polynomial the one you can see in the lower part of this slide here, you can rewrite this by using two vectors. The one that is containing these unknown polynomials, a0 and a1, and another one that is this polynomial 1 and x, nothing else. This, by the way, is already related to Truscall's triangle, but because I cannot write to my slide and I cannot explain this to you today. Okay, what's the information that I know? Information that I know is where these nodes are located when there is no deformation. So the first node is located point where the x is equal to 0, because look where the L and X are located. So at the node that is a left-hand side, x is equal to 0. Node that is a right-hand side, x is equal to L. So let's use that information. Now let's substitute that to this polynomial expansion we used. So we get two equations, two unknowns. Now we can represent this by using vector u's and polynomial coefficients. So something that is between is a matrix that we have to invert because we would like to solve the polynomial coefficients like it is shown in the last row of this slide. And once we have solved it, then we can substitute that back to the description of displacement. All right, now let me tell you a story. Now, this element here is having 2 degrees of freedom. And I don't know if you know my history. I think that I explained this history that I spent my postdoctoral time in Chicago, University of Illinois at Chicago. All right, so would you like to hear a story what happened to me in the very beginning of Chicago? Okay, so you don't want to hear it, so I'm going to tell it to you then. So what happened to me that I got this assignment, again, from this famous professor, Dr. Sabana, and he said that, okay, we are developing here a new plate element. It's a special kind of plate element because it consists of 48 degrees of freedom. I'm never going to forget the number 48 in my life. 48 degrees of freedom. What I would like you to do to me is that I would like you to create the safe functions for this 48 degrees of freedom plate element. So how you do it? Well, you just do it the same way we just looked at in this slide. So you get started from polynomial expansion, but not this time there was 2 components. In my case, there was 48 components. Okay? You use these 48 components and you do exactly what is shown here. You create this matrix that need to be inverted, and you substitute the information back to the description of displacement. Work done. But this element was very inconvenient. It was harder than this projector we have in the class because it was absolutely not willing to cooperate me. Every time that I build this matrix, 48 times 48, I invert it, it says singular. Singular, singular, singular. Day in, day out, singular. Week in, week out, singular, singular. No matter how I was changing the polynomial expansion, always, always, and always singular. And I spent, honestly, this is no extra Aki statement here, but this was an honest statement. I spent 3 months of my life, singular, 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 and I was started to lose my hope. And then it was all about, because there's so many different combinations, and I was pretty sure that the combination willing to work is not existing. One day, not singular. And I was able to make the element. The rest was a downhill, but sometimes it can be that painful. 3 months. Trying, and trying. Of course, I made it automatic, but still it was a lot of manual work to do. So it can be easy like the one that is shown here, or it can be complicated as in the case of 48 times 48 matrix. Okay. Now, once we do this substitution, then we can get something that is extremely important for us. So we get safe functions. Safe functions, as the title implies, are telling the shapes of displacement when we have a nodal displacement. So it tells me that if I have these left and right side nodes, so if I'm moving the left side node this direction or that direction, how are the particles between these two ends? How are they moving along with this displacement? And that one is described by using the simple linear polynomials. Now we have linear polynomials here, but in a general case, it's way more complicated than that. So it can be something that we need to make an assumption what the deformation should look like. Okay, so these safe functions are something that allows me to create all the properties that I needed in my computation. And those properties are stiffness matrix, which relates to forces and displacement. Nodal displacement and forces. And of course, I can create the mass matrix if I wanted to compute natural frequencies. Because natural frequencies, I need to know the mass and stiffness. Mass and stiffness, that relation is telling me how is the natural frequency and natural deformation modes. Or maybe it would be better to say deformation modes that are associated to these deformations. Okay, in this case, so it's kind of unrealistic to show what's going to happen to these particles between the two different nodes because it's going to be linearly distributed. So displacement will be linearly distributed. Very simple case. But again, the information that I was after is the one that is shown in the first equation of this slide. So I'm able to get this n, safe function matrix. Yeah, realize that is 1:30 already. So can you guys handle this if we go another 15, 20 minutes? Because no break so far. Is it okay? All right, so let's just, Dr. Esla, can you handle it? Very good. So let's continue then. All right, now comes next in class quiz, but I need to explain this to you. And how can I make the writing? Because right now I just need to do the writing here. I need to take a look if there's something else that I can somehow. Yep. All right, you see the writing now. Okay, very good. So look what we had in a previous slide. Let me take myself, I think that I can use this slide here. So it was two nodes like this, and each of them can move left and right. So this is a 1 degrees of freedom for each of these points. What's going to happen to my polynomial expansion if I keep on increasing the number of points that I'm interested in? So let's say that here in the middle I have a node which too can move left and right. So that would mean that I have a total of 3 degrees of freedom. 3 degrees of freedom. And remember how I started in my polynomial, so it was like this was the first component, this was the second component. Guess what will be the third component? A2 multiplied by x, what? Correct. Now if I would add more components here, if I would here put the 5 nodal degrees of freedom, what should I do to describe that? I can increase the number of polynomial components here. So it's going to be, let me add it here, A3, correct. And then like this, A4, x power 4, so on and so forth. This is what I did. Where this is coming from? Well, this is obvious, but in a three-dimensional case, and generally speaking, they're coming from something that is called Pascal's triangle. And this is very important in terms when we look how is the element properties and how they perform and how we know that how is their convergency properties. Pascal's triangle is like this. In two-dimensional space, it's like this. So this is x. Sorry, that is a little bit unclear writing. This is y. That's my first row or second row. And then I continue like this. And then I continue a little bit more like this. Okay, this is number 2. Okay. Now, look how I select my components here. I started here, so I need to take this one into account because this is the one that is describing the large, or let's say rigid body motion. So if you don't have the one, your element will introduce strains depending on its original configuration, and that's unrealistic. That cannot happen. This one here, this second component, the second row, I have to take into account too, because otherwise the element is unable to describe constant strain. And constant strain is another minimum requirement to make something that works in reality. Because constant strain, if nothing else, you can describe everything with a piece of constant strains. But then the rest is a matter of choices. You can do what I just did. You can select this one here like I did, but you can do also in a way that you're skipping the x power 3, and instead you can take x power 4. Now, if you choose to go like this, so if you're not taking all the polynomials in row as they are listed here in the Pascal's triangle, you will get the conforming or non-conforming elements. What's the trick? What's the big property here? What's the big benefit, perhaps? And the big benefit is that, if you're not choosing your elements according to the list, but you skip some of them, you might get the element that convergency rate is better than selecting them in a row. This is a little bit of a game that you need to check, and there are several different checks for each of the elements that allows you to do this checking. But typically what happens is that you're skipping some of the components, you increase the convergency rate. And convergency rate again means this. So if say that this is a cantilever beam is a very simple case. You can get correct solution using one element only. But let's say more advanced case. Let's say that the real answer will be u equal to 1, hypothetically. So this is a 1 here, and then this is here the number of elements. How many elements you need to get this absolutely correct solution? And typically the finite element is converging like this. And convergence you can check by taking two consequent solutions like the one here and here. And if they are not same, you can keep on increasing the elements until you will get the two solutions like this one and this one. You see no significant differences anymore. So you can be guaranteed that this is your converged solution. Minor problem is that certain elements, particular non-conforming elements, they may have a convergency property that is coming here, or they might even oscillate around the correct solution like this. Then it's not even guaranteed that you take one solution here, another solution here, and you accidentally can say that, okay, they're all the same. Still incorrect. Still incorrect. That's a very bad luck, but it can happen. It can happen. Okay, this one here is called Pascal's triangle. And this is how you select your polynomial coefficients. And as it sounds to be tempting to take the components in a row, that may not be the most efficient way to use in practice. And some of the well-performing elements, like my famous 48 times 48 elements, is not confirming, meaning that I was selecting this, and this, but then there were very high order components because they were the only ones that were able to do the things without singularity. Very bad explanation, but it gives a properties element that it was performing okay. Later, of course, we figure out that element too was suffering from these lockings that was being pointed by Jussi Soponen. Okay. So now I was able to do this writing. So let me take myself back here. Now, 4-node spring element where the nodes can move left and right only. What kind of polynomial expansion I can use? And the only one is correct. Now you need to take a look at the number of polynomial components. Okay, one only is correct. Which one is correct? So the Socrates is not on. This one. Four-node spring element shown below. Polynomial expansion for the element could be. Not necessarily, but one option. Other options are not possible. And why not? We're going to learn that momentarily. So, well, you can read by yourself because you see the slide, right? Right? Yeah, very good. Okay, Team Malaysia is voting what? Not easy. So this is not the easy game. And this is why we don't really score 100%. But that happened too last year. And there was a lot of dancing afterwards. Me dancing, they're watching. Okay, one all is correct. So what can be correct polynomial expansion? Okay, so Team Malaysia is voting A. So that's A0 plus A1 times X. Okay? Okay, oh, hold on. Sorry, I'm in a incorrect place. So this one. Oh, how come we got more students around? So now we have 15 students. Okay. Correct solution is D. D, because number of polynomial coefficients. This one. Because the number of polynomial coefficients, the number of degrees of freedom, not a decrease of freedom, not a decrease of freedom, must match. Otherwise, this is no go. Because what we wanted to do here, again, remember our mission here. So we have a mission. Our mission is here to replace this polynomial expansion, this polynomial coefficient by not a decrease of freedom. That's why the number must match. Very good, very good. Okay, so now what follows is that because now we have this information, so we can compute now stiffness matrix. We can compute everything else we needed. And the rest that is shown here is, I don't know if this is very important even, but this is just showing how the elastic forces of the spring element can be computed. You see that the elastic force is such that it is a volume integral over the stresses. I think that you can simply skip this. This is not so important in my mind. You know that the stress is equal that the displacement, the strains multiplied by elastic coefficient, which can be a matrix representation too. Now when using the virtual displacement, this can be expressed like this. Again, don't memorize this. This is not important for us. This is just the details of the finite element method. We don't need to know that much of the details. But what we do need to know is that how is that the strain and displacement are related. And we can compute this relation by using partial differentiation. You look at what I'm differentiating here, shape functions. So I must know the shape functions. I must know what is that I'm assuming the particles between the nodes, how they performing, how they behaving. Once I know that, it's going to give me possibility to compute this partial differentiation of the shape functions, and that's only that I need to compute my stiffness matrix. And my stiffness matrix eventually look like this. This is it. Again, let me summarize. So we started from defining the nodal degrees of freedom. So we realized that there was a 2 degrees of freedom element. So we described the displacement, all possible location, because X started here, all possible location, not just the ends, but all possible location by using polynomial expansion. And we realized that polynomial is not the way to go, because these guys, they don't represent anything physical. So their physical interpretation is non-existing. So I'm not happy. So I wanted to make this to be more user-friendly. What I did was that I replaced them by, say, functions. And what happened then was that I was able to express, again, the displacement in all the points, not just the endpoints, but all the points by using this shape functions, a vector of nodal coordinates. A vector of nodal coordinates was this guy here and this guy here, nodal points. This is a vector or matrix shape that tells me the displacement wherever I'm going, wherever I'm going. Okay? Then I was able to relate this one with strain, and that was able to, that was something that was needed to create my stiffness matrix. And the finite element modeling most often is all about solving this. This is this stiffness matrix. This is nodal displacement. This is external applied forces. And what I wanted to do here is that I wanted to solve nodal displacement. And it goes like this. I am inverting my stiffness matrix, multiply that by external applied forces. That's it. Okay, how significant this is for us? Pretty significant, because remember what we were after in the very beginning. So it was this kinematic section that we were after. This displacement is this guy here. Okay. All right. Any comments, questions? Pretty clear. Anything you wanted to discuss? Are you still? Yes, yes, sir. By the way, before you answering that, let me tell you what happened to me earlier today. I made a visiting lecture in a Jussi Sopanen's class in a pastoral level, first year students, and they asked me a question. Correct. You heard it. You heard it right. So they asked me a question. I was so emotional. I started to cry and everything. I forgot to answer the question, but it was a big deal. Big deal for me. Now back to you.
Does inertial tensor affect point mass of the flexible body?
Okay, so the answer. So the question is that what about the inertial tensor? Okay, how that is affecting to point mass of the flexible body? Okay, this is so difficult question that it needs several weeks before we're able to answer it. But your question is basically that if we have a body like this body have an inertial tensor, right? And then this inertial tensor is the one that is describing the inertial properties of this body with respect to reference coordinate system. Now you're asking about what about the point masses and what about the whole business about how this all is related to these nodal points and nodal point masses. That's what you're asking. This is very, very complicated question, so you can make a dissertation, doctoral dissertation, not the master thesis dissertation, but the doctoral dissertation to address this well. How it goes such the way that we have to describe this element instead of this inertial tensor, which is like a continuous representation. We're going to describe the body by using points. And if we're adding these points enough, then the inertial properties becomes to be good approximation, but just a good approximation. So it's never going to be mathematically match. It's never going to be that. Maybe it can be a mathematical match if you come and do your doctoral dissertation in a way that you can make a match. But it's going to be, it's still something that I can see papers published in this subject matter. So it's not the simple thing. Because what we do here is that we're compromising the inertia description. Okay, what's important in dynamics? Inertial forces and externally applied forces. Now, if we're compromising inertia, is that as serious? Yes, it is. It is serious. But in practice, the difference is not that bad. So we can still live with that. Very good. Mustafa is here, so are you saying that we need to go? My lecture? Oh my God, this is too much. So each of us are. So should I go also as one lecture here? Not mine, but something else. Okay. Hey, I need to go back to my room to be there at 2 o'clock. So this is where we continue. But now you got a little bit of what is a finite element method. This is something that you guys are already familiar with. Very well, because next will be a bit more advanced. Not much. But we're going to take a look at the beam elements. Here's a beam element. Beam elements, the shape functions and polynomial expansions making more sense. They are more clear. All right, so that's where we continue then on, what is it, Tuesday. Tuesday, by the way, will be the last lecture prior to midterm exam. So on Tuesday, you're going to get the list of questions. And if anything unclear, you can ask. And you can also vote which question you would like to see in the exam paper for 100% certainty, which question you would like to take it off. Again, 100% certainty. So voting will be organized next week. All right, see you on Tuesday then. Oh, I need to close this streaming and recording and all this kind of stuff.